Okay, today we're going to talk about heat. If you remember last time we were talking about energy. And energy is the ability to do work or produce heat. We talked about heat last week or in the last video. So today what we're going to focus on is heat. So here's a good definition for heat. It's the flow of energy from an object at a higher temperature to an object at a colder temperature. So it always goes from high to low temperature. So heat is this energy that flows from a hot object toward a cold object. So it always goes from hot to cold. So when you imagine like you're outside on a cold day like this and you touch a doorknob, okay, and it feels cold. Why does it feel cold?
The heat's getting sucked out of your hand.
Yeah, it's because the heat is leaving your hand and going into the doorknob. You're losing heat. So that's kind of a little bit different way to look at a cold object. It's not cold because it's cold. It's cold because you're losing heat. If that makes any sense. Okay. But we're going to talk today a lot about heat. And heat flows from the hot to the cold object, but it flows three ways. It can flow by conduction, convection, or radiation. And I've got a picture over here. We'll talk about that in just a second. So heat energy is transferred between objects because of temperature difference. Remember, it always goes from hot to cold. So that's what heat is. It's this flow of energy. It's a flow of energy from the hot object to the cold object. Always from hot to cold. All right, heat transfer. Heat is transferred from one object to another in three ways. In one of three ways. Conduction, let's talk about that one for a second. Conduction is when you actually physically touch. So this stove, this pot on the stove here, if you were actually to touch it and the heat is going from the pan into your hand because you touched it, that's conduction. Okay? Number two, convection. Convection happens when heat is transferred through a fluid. So if this was a pot of water, the water inside, on the bottom it's obviously very hot because that's the part that's on the stove. But as water gets hot, the molecules expand, which becomes less dense, so it rises. Okay, and it causes these convection currents. It goes up and cools, it comes back down, it gets heated up and goes back up. And so these convection currents here. So what convection is the transfer of heat in a fluid. Number three, radiation. Radiation is where heat is transferred from one object to another through space, so over a distance. Okay. We're going to go into each one of these in more detail. Let's start with conduction first. Conduction is the transfer of heat from one object to another by direct contact or touching. So you have to actually physically touch the other object. An example of this is touching a hot pan. The heat from this pan is going to go into your hand. So it's at a higher temperature than your hand. And you can burn yourself this way, right? If there's a lot of heat in that object, it goes into your hand very quickly and it can cause you, it can burn you. So just remember, conduction means you have to be touching in order for that heat energy to be transferred. That's the key there. Okay, let's go to convection. Convection is the transfer of heat from one object to another through a fluid. Okay, and a lot of times when we think of fluid, we think of it has to be a liquid. But actually air is a fluid. And so examples of convection are a pot of water. We see these convection currents. It gets hot because it's on the stove right here. So the water, when it gets hot, the water molecules expand, which makes it less dense, and causes these convection currents here. It comes back down, and when it's heated, it goes back up. So that's one example. Another example, though, is magma in the Earth's mantle. Going back to, I think you guys had this in 7th grade where you learned about the different layers of the Earth. Okay, what do we call this very outside layer? The crust. It's very thin compared to the other layers of the Earth. What's underneath the crust? This layer called the mantle. Okay, it's made up of of different parts as well. But the mantle is right underneath the crust, and it goes down until you reach the core. Well, the Earth's core is a really high temperature. It's very hot in the core of the Earth. And what that heat is transferred out, because through conduction it's touching the mantle. And the mantle is made up of magma. And from what I have read about magma, it has the consistency of like peanut butter. And so it's very thick. When a volcano erupts, it's the magma that comes out that's the lava, right? So it's very thick and it's really hot. Well, if you look at the magma here, by the core it's really hot, so it's going to cause those molecules to expand and it rises. Okay, well, it causes these convection currents. In the magma, this mantle part of the magma is like peanut butter, and so it's kind of churning underneath the crust. Well, what does that cause, this movement of the mantle, or the magma in the mantle? What does that cause?
Tectonic plate.
Yeah, it moves tectonic plates that are sitting on the crust right here, right? So this moving of this magma here can move the tectonic plates. And what do we call the movement of a tectonic plate?
Earthquake.
It can cause earthquakes, right? It can cause earthquakes. And so tectonic drift, yeah, and it can cause earthquakes. So if you look here, if it's coming up and swelling up right here, you're going to cause a mid-ocean ridge, right here, a valley. But where they collide, if they collided, say right here, it can lead to a mountain range right there. And so these tectonic plates push up against each other. And but anyway, that's another example of convection. So earthquakes are caused because of convection that's happening in the mantle. All right, let's talk about the last way that heat can be transferred from one object to another. It's called radiation. Radiation is the transfer of heat energy over a distance. So it's the transfer of heat energy over a distance, and actually it can even occur through empty space. Through empty space. The best example of radiation is the sun. When you go outside on a nice day, you can feel that heat energy, right? It's warm. And so when you look at it here, radiation can even travel through empty space. It travels through space as a wave. We'll talk about electromagnetic waves in the next chapter, but for right now, just imagine that it's a wave and it travels to the Earth. And so that's really what radiation is. It's the transfer of heat from one object to another, even through empty space. Okay. Practice problem number 6. I want you guys to try this one. It says, explain how ice helps lower the temperature of your soda. Draw a picture and show the flow of heat. So let me help you get started. Here's your soda. Your favorite kind, whatever you like. Okay, and it's filled up with your favorite soda here, and we put ice in it. Okay, so this is a big giant ice cube. How does ice help lower the temperature of your soda? Knowing what we know about heat and how it flows.
Absorbs heat.
Yeah. The ice, what temperature is the ice at, guys?
32.
Yeah, if we do, let's do Celsius.
0.
So 0 degrees Celsius. It's freezing, right? Okay, what temperature is your soda when it comes out of the fountain?
About room temperature.
Yeah, about room temperature. What is that? About 22 degrees Celsius? Okay, that's about room
Why are we
temperature.
doing Celsius?
Because we're in science, and we use the metric system in Celsius, really, for temperature. Okay. So which way is heat going to go? I want you to draw the arrow
Into the ice cube.
that shows the direction of heat flow. Remember, it always goes from a hot object to a colder object. So the temperature of your soda is higher, so that heat is going to go into the ice cube. Well, what does that do when you're taking heat away from the soda and it's going into the ice cube? Yeah, now it's not at 22 anymore. What temperature could it be at? Is it going to be higher or lower than 22? Lower. It might, I don't know, it might even get down to like 15 degrees Celsius or maybe even lower than that. And so what an ice cube really does is it's like a heat sink, a heat sponge. It pulls in all that heat. But will this happen forever? No, by the ice absorbing that heat, what's going to happen to that ice cube? It's going to melt. And so if you left this for the space of, I don't know, maybe 8 hours or so, and you look at it 8 hours later, what's going to happen? There's not going to be the ice there, is there? If the temperature in this room was 22 degrees Celsius, what temperature is your soda going to be at? 22. Well, it was at 15, but because the temperature in the air is higher, it's going to go into the soda until it reaches this equilibrium point, and your soda will end up at the same temperature as the air in the room. And so think about, when you think about these problems, guys, heat is always flowing from a high temperature to a lower temperature. It's always flowing. So anyway, that's kind of how ice works and how it helps lower the temperature of your soda. Okay, here's a couple of terms I hope that you're able to define after we're done. Temperature and heat. A lot of people think they mean the same thing, but they're much different. Okay? Let's contrast them with this slide. Temperature is a measure of the molecular motion. So it's a measure of kinetic energy, how fast the molecules are moving. Here's the deal. The faster the motion of these molecules, the higher the temperature. So on a hot day, say it's a summer, you can reach 100 degrees Fahrenheit, right? Okay, if we put that in Celsius, I don't know exactly what this is, around 38 or something, somewhere around there. Maybe 39, 40, who knows. How would you describe the air molecules on a hot day? So how would you describe the air molecules and their motion on a hot day if it's really like a nice day in the summertime, 100 degrees Fahrenheit? Are they moving fast or slow? Fast. If you contrast that to today where it's freezing outside, the air molecules are moving very slow. And so a thermometer, all a thermometer does is measure how fast the air molecules are moving. Okay? So it's a measure of how fast they're moving. Heat, though, let's contrast that to heat. Heat is the transfer of that kinetic energy from a warm object to a cold object. So heat is the flow of energy from hot to cold. Temperature just measures how fast the molecules are moving. Okay, let's talk about this one. Practice problem number 7. It says, below is the floor plan of a house with 4 rooms, all on the same level. Using arrows, show the direction of heat flow from room to room in the house. Let's go from room 1 to room 2 first. There's a door right here. That's what this space right here means. There's a door. So air can flow from one room to another. Which way would it go, guys? The heat? We're talking from room 1 to 2. Which way would the arrow be drawn? Yeah. Always goes from high temperature to lower temperature. So the heat is going to leave room 1 and go to room 2. Okay? Let's go clockwise here. Room 2 and room 4 are connected through this door. Which way is heat flow going to occur?
4 to 2.
Yeah, it's going to go from 4 to room 2 because this is 75 and this is 72. Higher to lower. Heat always goes from high to low. Let's go from 4 and 3 now through this door. Which way?
Left. 4 to 3.
Yeah, it's going to go to the left here. Again, because 75 is higher temperature than 70, heat always flows from high to low. And what about room 1 and 3 now? Yeah, it's going to go down. Okay, because this one's 80 and this one's 70. But if you let this go for a while, what temperature will they all reach a common temperature?
72.
The average temperature would be what, around 74 or something like that? You could figure it out, right? What is it? 74.25. So perfect. You let this sit for a while, and they're all going to be about 74. Okay. All right. Architects, when they're planning a large building like this building that we're in, how could you use this knowledge of heat flow to create a very efficient building? I guess what I'm asking, like if you're building a school, where's the most efficient place to place the kitchen? Would you want your kitchen to be on this corner right here, so the corner of the school? If you put it there, wouldn't heat flow be lost to the walls and heat is going to be leaving through the walls there? So if you were going to design a really efficient school, where would you put the kitchen? Yeah, in the middle. Because in our kitchen, they're constantly cooking food, and from the ovens and stove, there's a lot of heat being released. Wouldn't that be more efficient if you put it in the middle of the building and then the heat is released to the different areas of the school? Sure. So you can think about this knowledge of heat flow, and use that to make more efficient buildings and houses. And think about the flow of heat from one place to another. All right. Now I wanted to finish up with this idea of heat. I wanted to go back to how we get energy. We ourselves get energy. Somebody explain to me how we get energy. We eat food, right? What about water? Does that give us energy? Nope. Water has 0 calories. But if you drink a soda, would that give you energy?
Yeah.
Sure, it's got calories. So you've got to take in something with calories. So you eat or drink something with calories. But does that give us energy just by eating it? No, so explain it to me. How do we get energy from that? Okay, it goes through your digestive system. Your teeth, you chew it up, you break it down, you swallow, it goes to your esophagus. Then your esophagus goes to your stomach. Is that what gives you energy when it gets to your stomach? Nope.
It breaks that up and puts it in the source.
Good. The stomach just breaks up with stomach acid. It breaks it up even farther. And it goes into your small intestine. Is that what gives you energy? No. So what happens in the small intestine? Yeah, those nutrients now are broken down, really small molecules. And where do those molecules get absorbed into? Into the bloodstream. So from your small intestine, it goes into the blood. Okay? And then once it's into your bloodstream, where does it go?
Everywhere.
Yeah, into all of the cells of your body. There's trillions of cells in your body. And those nutrients now are in the blood, and they go to your cells. But when they get to the cell, what happens?
Mitochondrial cell eat it.
Good. The nutrients go into the cell and go into which part of the cell? The mitochondria. Okay? The mitochondria takes in those nutrients and it converts that nutrient into what? Into ATP. ATP is the molecule of energy for our body. ATP. You guys remember from biology? So ATP is then used to do work by the cells. And so everything that we do, every movement we make, has to use some sort of energy, and it uses it in the form of this molecule right here, ATP. I think I've got a picture of it right here. This is what the chemical composition of ATP looks like right here. This molecule right here is called adenosine. And so the A stands for adenosine. The T stands for tri. What does tri mean?
Tristan?
It means there's 3 of them. And the P stands for these phosphate groups. Notice how there's 3 phosphate groups right here that are attached to this adenosine molecule. How the body gets energy, guys, is you eat food. It goes to your bloodstream, it goes to your cells, it goes to the mitochondria. The mitochondria is what's making ATP. This is the energy molecule of our cells. But just making it costs energy. How do we get energy to move and to talk and to think? How do we get that energy? Well, we break this chemical bond right here in between this third and second phosphate group. We break it. That releases energy. And so our muscles can do work, and we can think, we can talk, we can breathe. when you cut that last phosphate group off, it's not adenosine triphosphate anymore. What does it become? Adenosine diphosphate. So this D right here stands for diphosphate. Notice that there's only two of them here.
Nuclear reactors.
What's that?
It breaks the bond and makes it.
Yeah, well, this is a chemical reaction, though. It's not nuclear. So once it's ADP, then it goes. You have to eat food. You get the energy from food, which puts on another phosphate group right here and becomes ATP. Then we break it whenever we need to do energy for work. We break that bond and it gives us energy. And so I just wanted to kind of finish with that. Energy is the ability to do work and produce heat. Guys, a lot of the energy that we get from food doesn't actually go to helping us do like movements. A lot of it's going to help heat our bodies up. A lot of that energy is turned into heat energy. What temperature is our bodies at right now? 98.6. What's the temperature of this room?
70.
About 72 degrees Fahrenheit. So how come our body is such a higher temperature than the room? Because our bodies are producing heat through this process, metabolism. Okay, when we're making ATP and we're burning it, and it's releasing a lot of heat. So how come in the wintertime do you guys like to do we wear coats and wear a lot of layers? What are we trying to do? We're trying to trap that heat into our body, because it's our bodies are higher temperatures, releasing heat into the air around us. So by wearing coats and many layers, try and trap that heat next to our bodies. So anyway, that's kind of how it works. So energy is the ability to do work or produce heat. And so hopefully you have a better understanding of heat now.